Okay. So obviously I prefer that you be on live if you can. There's going to be times that, you may, if I'm doing it this way and you're really not feeling good or something like that, I will record it. Or like in Carter's case, he was doing a college visit today, and that's fine. Like I said, so we do need to follow DMAX schedule also because it is a DMAX course, but then we also didn't meet on Thursday, so it's kind of a makeup day for not meeting on Thursday as well. So John, what's your update?
Oh, like quarantine?
Yeah.
I'm quarantined till October 1st.
October 1st, is that a Thursday?
Yeah,
Or what?
Thursday of homecoming week.
Okay. That's good. So you could come back to that. What about you, Jack? Is that same date?
No, I get out earlier. I think mine is like the Tuesday of homecoming week.
Okay. So it kind of be, all right. Sounds good. And as far as for the rest of you that I really don't care because we can use the chat function. Like I don't care if you're in the room, that's great. If you're more comfortable being in study hall, having ear pods in or something like that, I'm okay with that too when we're doing it this way. But really what I'd like to do, I'll probably stay remote because it's just a little easier on me too when I want to record the sessions. But anyway, we'll do this for a while, get through this time, and I guess go from there. So it'll make. Sometimes you got to go through some adversity and make you stronger in life. There's a lot worse things that could be going on right now. So just remember that, keep it in perspective, and learn. I guess get better as we go, right? So, any questions for me? I know there was the limit epsilon delta stuff is probably the most awkward until you get good at it stuff that you're going to be doing. It'll get a lot easier as far as computations and calculations and different stuff like that going forward. But how's that going? Is everybody good on that, or is there a specific question as you're trying to work stuff out on that? You're all good? Okay. Can we do number 31? Hopefully. What is that in section 1.5?
Yeah.
Okay. And then we'll get into that. And like I said, once we're into chapter 2, I do have video instruction to make it easier too, if we have to keep doing stuff like this. Yes, I was going to do some examples like that today. So we'll keep that one in mind. I'm going to do one like it, and then maybe you can try it too. So anyway, I'll go ahead and get started. Basically, all I did is give you some theorem results, like limit of the sum of functions is the sum of the limit. The difference is the difference of the limits. Limit of the product is the product of the limits. Limit of the quotient is the quotient of the limits, as long as you're not dividing by 0. So I'm going to finish up a couple of those and then look at some specific examples like that. I'm bleeding all over from where that walleye cut me last week, all over my notes. But you see red streaks, it may be blood, not my pen color. All right, so we'll do that. Let me go and just get into the Blackboard. I appreciate you being live on your day off of school. And so here, let's look at a theorem. Proven fact, once again, is a theorem. We're going to let the limit as x approaches a of f of x exist and equal L. So remember, we're only looking at limits of functions here. Then the limit as x approaches a of f of x to the nth power is going to equal the limit as x approaches a of f of x quantity to the nth power. Isaac, I see you joined, so welcome to the group. You didn't miss much yet. We're just getting started. So that's to the nth power, which is going to equal L to the nth power. So the way the way I remember this one is the limit of a power is the power of the limit. So that's kind of the shorthand lingo, the way I think of that. Let's just look at a real easy example here of this one. So it looks like we're looking at a red example. We're going to look at the limit as x approaches 2 of x to the 10th power. Okay. Well, we know that the limit as x approaches 2 of x exists and equals what? What does this equal? This is the identity theorem. The identity. As x approaches 2, what's x approach? You should all be saying 2, right? So then that implies that this equals limit as x approaches 2 of x quantity to the 10th power. And so that's from limit of the exponent equals the exponent of the limit. So instead of power, because that's product, I should have go back. Instead of saying the limit of the power, power starts the same letter as product. So instead of doing that, we're going to call it an exponent. So the limit of the exponent is the exponent of the limit. And anyway, so what's this equal? This is going to equal, so this thing right here is going to equal 2 to the 10th power would be the final answer. Of course, we should all know that's 1,024, right? If you double something 10 times, you get 1,024, I believe, right? So anyway, you can verify that if you like. But anyway, so it's 1,024. So that'd be the limit as x approaches 2 of x to the 10th power. So that's one way to use that. And then we can have some different things as well. So let's look at some examples here. We're going to look at we'll go ahead and start with, let's do number 23 first, and then we'll go into 31 for Kylie. All right, so the limit 23 is the limit as x approaches 4 of the cubed root of x squared minus 3x plus 4 all over 2x squared minus x minus 1. Okay, so in this case, I can say the, did we have limit of the root as the root of the limit yet? I don't know if I gave that one to you. So since an exponent, you know, if I have a square root, that's like an exponent, that'd be like to the 1/2 power, right? So really, we can also say the limit of the root is the root of the limits. So we also have that theorem. I'm not going to write that one out, but basically it's for the same reasons. We have limit of the exponent is the exponent of the limit, because I could write this quantity in here underneath the radical to the 1/3 power, right? So I didn't have any restrictions on what kind of exponent it was. So anyway, the limit of the root is the root of the limit. It'd be the shorthand way to say this. So this would be the cubed root of the limit of what's underneath, right? So if I could take the limit of what's underneath, I could also say the limit of the quotient is the quotient of the limit. So I can kind of show my work here. And so I'm going to take the limit as x approaches 4 of x squared minus 3x plus 4 all over limit as x approaches 4 of 2x squared minus x minus 1. And if that, and I don't have an assistant here this week either, so I'm going to try and kill my phone over there. But anyway, we got the cube root of all this stuff here. Just cube root of the limit underneath. So if I do that, and then what I can, sorry about that. Anyway, so if I do this, then the limit of the sum is the sum of the limit. Limit of the difference of the limit. Limit of a constant times a function. So we could split this up if we want, saying the limit of the sum is the sum of the limit, etc. Limit of the difference is the difference of the limit. Long story short, what I'm going to let you do is if we have a polynomial, we're actually going to be able to plug those in, right? So we're going to, limit as x approaches 4 of x squared, I plug in 4 and get 16, right? So I can plug it in there. So if we have a polynomial, then what we're going to be able to do because of those limit theorems is we're just going to be able to plug in. I will let you do that. Normally I make everybody write that out, but since we're doing some remote stuff, I'm not going to make you do that. If we get to a polynomial, all those things would apply where this is a nice function and we can just plug it in. So this is going to end up being the cubed root of, on top, 4 squared is 16 minus 3 times 4 is 12, so 16 minus 12, I'll just do one more step, and then plus 4, that's on top, that limit. The bottom limit, 16 times 2 is 32, minus 4, minus 1, and so this is going to equal, that's 4 plus 4, this is going to be the cubed root of 8 divided by 20 minus 1 is 27, so it's going to be the cubed root of that. Of course, the cubed root of a over b is a cubed root of a over the cubed root of b. So cube root of 8 is 2, cube root of 27 is 3. So the actual answer for this limit is 2/3. So hopefully that makes sense. So put a little check mark by my answer there. Anyway, that would be the answer in the back of the book. So we split it up. Limit of the root is the root of the limit, and then limit of the quotient is quotient of the limit. Then I can use the sum and difference of functions. I can use the exponent rule there. I can use limit of a constant times a function here. Limit of a constant is a constant, right? So I could do that too. In fact, I'm gonna do that. So if we really wanted to show that, if I had what I had x squared plus 3x minus, minus 3x. The top one was x squared minus 3x plus 4. And if I took the limit as x approaches 4, like I say, limit of the sum is the sum of the limit. So I'm only going to do this. Limit of the difference is the difference of the limit. Difference of the limit. And so this would be the limit as x approaches 4 of x squared minus the limit as x approaches 4 of 3x, and then plus the limit as x approaches 4 of 4. And then if I do that, then I can use different ones here, right? So now this is x to a power, so I can say the limit of the exponent is the exponent of the limit. And then I would have, so the limit as x approaches 4 of x, quantity squared, right? And then I'm going to use a different color for this one. So then be minus, this would be limit of a constant times a function is the constant times the limit of the function. And so this would be 3 times the limit as x approaches 4 of x. And then, of course, then we'd have, let's see if I got enough colors, plus the identity as x approaches 4, or excuse me, not the identity. Limit of a constant is the constant, right? So as x approaches 4, what does 4 approach? Well, 4 doesn't move, so that's just 4. So the answer to that one is 4. As x approaches 4, 4 doesn't move. So the limit of the constant is the constant. And then, of course, on these next two, we know that, going back to red here, as x approaches 4, right? So that equals 4 That's going to equal 4 squared, but that's 4 inside of there because of the identity. Limit as x approaches 4, x approaches 4. So that's the identity for that one. So that's 4 squared. And I'm going to keep with my color minus 3 times, once again, this is the identity. So 3 times 4. So that's the identity here, getting to that one. And then plus 4. So if I do that, 4 squared, 16 minus 12 is 4 plus 4. That gives you the top one actually equals 8, right? That was the numerator. And so you can see if we have a polynomial, we can break it down using those limit theorems every time. So I'm going to let you, if it's a polynomial function, you can just plug in, okay? So that would be a lot easier than trying to write all these steps out. But mathematically, this is excruciating detail of why the numerator was 8 under the cubed root. All right. So now let's go to number 31. Number 31 was the limit as x approaches 7 of x squared minus 49 over x minus 7. Now here, if you said, hey, the limit of the quotient is the quotient of the limit, and then it's a polynomial, right? You might just plug in. And if I plug in the numerator, I'm going to get 7 squared is 49 minus 49, I get 0. If I plug in the denominator, which is also a polynomial, I'm going to get 0. So 0 over 0 is what? This is indeterminate, right? So this is one that we need more information because it's indeterminate. So the question is then, what do we need to do? So what we need to do is we need to manipulate. If you get 0 over 0 form, we need more information to know what this approach is. If we were to graph this thing, remember, this is my function. This is f of x. So f of x is not a polynomial. This is a rational function made up of a polynomial on top and a polynomial on the bottom. But the domain of f is all reals excluding the set containing 7, right? Because it's not okay to plug in a 7 here because I'd be dividing by 0. But remember, the limit as x approaches 7 from above and from below is I can get as close as I want without touching it, right? So if I do that, what I need to do is I manipulate this. If I factor this, I'm going to rewrite it. I run out of room here. So I have the limit as x approaches 7. If I factor it, I can write it as x plus 7 times x minus 7 all over x minus 7. So the difference of 2 squares, right? And then doing that, what I know, by the way, it is exactly equal to this because all I did was factor it. But then if I try and cancel these out, then I can say it's equivalent to the limit as x approaches 7 of x plus 7. And why is it only equivalent and not equal? Because I actually changed from what was my function f of x, which is the domain of f was all reals excluding 7, to just a simplified version away from 7. So remember, this is only equivalent on the domain of f. Okay, so if x actually equals 7, it's a problem. But in this case, I can go ahead and plug in, and I can say that it's a polynomial. So just plug in, or I could say the limit of the sum is the sum of the limit and the identity for the first one. But anyway, this ends up being 7 plus 7, which is 14. So the answer is 14. Remember, if we were to graph f of x, basically if I plug in 0, I'd be up at 7. If I plug in 7, I would be up at 14, but that's actually a hole. So what happens is this is equivalent to the graph of a line with a hole at over 7 of 14. So the range of f is you're going to hit all heights except the height of 14. Okay, but notice the limit from the right. So as I approach from the right, I'm approaching that height. As I approach from the left, I approach that height as well. So the right-handed and left-handed both exist and are equal. The long story short, if you end up with a 0/0 form, what we need to do is we need to manipulate. So 0/0, we need to manipulate. And what's one way to do that? One way to do that would be to factor. That's what we did on that one. We factored and we're able to eliminate some terms. Another thing that we could do is multiply top and bottom by the conjugate. So I'm going to show you one of those as well. And what's the conjugate mean? The conjugate of A plus B is what? Anybody know? A minus B. It's the same, it's a binomial with the same thing with an opposite sign, right? So let's look at one like that. So that's another thing that we may do. The last thing we want to do is plug in close to. Okay. So coming back, let's do number 43. So these odds are good practice. So if I want the limit as, is this N or H? H, I think. Limit as H approaches 0 of the square root of H plus 2 minus the square root of 2 all over H. Okay, so if I said, hey, the limit of the quotient is the quotient of the limit, and then limit of the difference is the difference of the limits, and then plug limit of the root is the root of the limits, I could do all that. So limit of the quotient is quotient of the limit of the difference is the difference of the limit, and limit of the root is the root of the limit. And if I did all that, what do you end up getting? If I plug in 0, long story short, I get square root of 2 minus square over, or over square root of 2. I end up getting 0/0, right? So 0/0, once again, this is an indeterminate form, so I need to manipulate this. So what I can do then is I can multiply top and bottom by the conjugate. I wish I could just eliminate part of the board, but apparently I don't know how to do that. So this is the limit as H approaches 0. So I had square root of H plus 2 minus the square root of plus square root of 2, sorry, all over H. So if I multiply top and bottom by the conjugate of the numerator, that'd be the same thing with the opposite sign in between. Remember, this is A, this is B. So step plus B, sorry, it'd be a minus B, minus square root of 2, all over the same thing. So I can multiply top and bottom by the same thing. So this is the conjugate of the numerator is square root of H plus 2 minus the square root of 2. So that's minus there. The top and bottom here and here are the same. So look at the bottom one for what we're multiplying through by. Now, if I do that, then what happens? We're going to FOIL this out. So that's first times first. So this ends up being the limit as H goes to 0 on top. Square root of A times square root of A is A, right? So this is just H plus 2 for the first times first. And then the outer is plus square root of 2 times square root of H plus 2. And this is, excuse me, minus, because that's a minus there. And then plus square root of 2 times square root of H plus 2. Those cancel. So the outer and inner terms cancel. And then last times last, if I do that, would be square root of 2 times square root of 2 is, and then one's positive, one's negative, so it'd be minus 2, right? All over. Now on the bottom, I do not want to multiply this out. I want to leave factored, and you're going to see why. So if I leave it factored, I'll have H times H plus square root of H plus 2 minus square root of 2. So by not multiplying those out on top, what happens is I end up having some things cancel out, right? So that 2 cancels with that 2, and I'm left with an H on top. So this is equivalent to, I haven't taken the limit yet, but I've got H over H times what's in parentheses. These H's would also cancel out, but they'd cancel out to a 1. So this ends up equaling or being equivalent to the limit as h approaches 0 of 1 over square root of h plus 2 minus the square root of 2. And then if I do that, now I can say limit of the quotient is the quotient of limit, limit of the root is the root of the limit, etc. Basically, I can just plug in h equals 0. This is a square root of 2 minus square root of 2. I did something. I got my signs messed up. Was the original a minus sign here? It was. I messed up my signs. Let me go back. I'll make my corrections in, trying to see what color I have left. Corrections in gray, I guess. Anyway, this was supposed to be a minus here. So that made that a plus here and a plus here. And then doing that, this all ends up the same, but that's a plus here. And then that's a plus. Otherwise, I'd be dividing by 0, something getting close to 0, which approaches infinity. I don't want to do that yet. Anyway, so I get 1 over square root of 2 plus square root of 2 is 2 square roots of 2. So that would be the limit of this one. So I apologize. I had the original problem for number 43 wrong. It was a minus sign for my function. Okay. Anyway, this is the height that you approach for that. Notice that also, if I had 1 over 2 square root of 2, that may or may not be the answer in the back. Make sure that, you know, if they have square root of 2 over 2 times 2 is 4, if they have this is an equivalent answer, right? So I don't care, personally, I don't care if you have the black answer or the circled answer that's in blue. They're both correct for me, as long as they're simplified. You wouldn't want the square root of 8 because I could write that as 2 square root of 2, right? So I don't want that. But anyway, so does that make sense on that? So what did we do on that problem? We took, we had the square root of h plus 2, and it was supposed to be a minus the square root of 2 all over h. And what we did is we multiplied top and bottom by the conjugate there. So that was a manipulation factor because that was 0 over 0. Long story short, we rationalized the numerator. So you remember rationalize the denominator, like when I had 1 over 2 square root of 2. The only reason you ever rationalize the denominator is to find a limit. So that's why I don't care if the square root of 2 is in the denominator. You don't have to rationalize that. But in this case, I'm actually rationalizing the numerator by multiplying top and bottom by the conjugate to get rid of square roots. And the reason that we rationalize is to find a limit. So something that you had to do in grade school or junior high math, not only because you can, but then because you're going to find a limit. All right, little timeout for questions. That's some odds. Hopefully those odds help. Is there any other exercises that you were working on that you might need help with? Let me go back. Isaac, I see you're on there. Can you give me an update? What's your status? Wait a minute, I guess I'm sharing my screen.
What's that?
There. What's your status?
Yeah, I'm good. I don't sound the greatest. I tested negative though, but I'll still have to quarantine. Wow.
You tested negative, did you?
Yeah, but I'll still have to quarantine.
Okay.
Yeah. So. Oh.
No, is yours October 1st also?
Yeah, that Thursday. Yep.
Okay. All right. Sounds good. And I know you probably missed Friday. We didn't meet Thursday, but if you missed Friday, that's recorded. So if you go under course content, Blackboard Collaborate, there's a thing in the upper left like when you're looking for like a session that I didn't have ready today, I forgot I didn't have that done yet, because I did a different time. You can actually click on that, and I'm labeling the sessions by the date just to make it easier on anybody that would miss or not be able to participate.
Good.
And you can go back and watch what we did Friday, and then if you have questions, utilize WhatsApp or whatever, or email,
Okay.
things like that. I mean, if it's something that you're like, hey, this only applies to me, I really don't care if my calculus class students text me. You can text me too. Some teachers really get irritated by that. I just want you to be able to communicate with me, right? If it's something that other people can benefit from, throw it out on WhatsApp.
Okay.
All right, and that goes for everybody. So, all right, so we'll keep going with the project and stuff. All right. Anyway, so I will be presenting this way for a while. I mean, at some point in time, we got to have a major quiz or a test. For tomorrow, what I'd like you to do is have 1.4 and 1.5 evens written out. It's better to use pen because if you try to scan it as a PDF, pencil doesn't work very good. It's hard for me to read. It comes out very light. So use a pen on your homeworks. You can use different color coordinations or whatever, and then email me a PDF. My email, everybody should have, it's on your syllabus, but it's just tjryle@dmac.edu. And you got to be careful because if you're on the DMAC website and just try and look for my email, my brother is an adjunct instructor too, so he pops up too. So you got to make sure it's tjryle@dmac.edu. So tomorrow I want the evens for 1.4. There's only one of them, and then 1.5 due. That epsilon delta argument in detail. All right, didn't see any other questions come up, so hopefully you guys are getting the gist of it. All right, can you see a whiteboard? Hopefully.
Yeah.
All right. So there's a couple other things. If I have a squared minus b squared, how does that factor? I'm going to have you factor all these. A squared plus b squared. I don't think I did this with you yet, did I? A cubed minus b cubed and a cubed plus b cubed. So I want everybody to try and factor those real quick. And then I'll move on to 1.6. What'd you guys do to Hannah? Wonder if Hannah was thinking, hey, I bet I could sneak out of here. He wouldn't even notice. Busted. All right. You got all these? Go ahead and put your voice boxes on, your talk. What does the first one factor?
Yeah.
As?
A plus B and then A minus B.
A plus B times A minus B, correct. So everybody should get that one. What about the second one? So I call this D2S. I call this the difference of two squares. What about the sum of two squares? Does that factor? Anybody? Not sure. D and F does not factor. Okay, this does not factor. So the sum of two squares does not factor. How about a cubed minus b cubed? Anybody got this one? Nobody? This is a chance to shine. I'm going to show you how I think about that. I'm going to focus on the a minus b. So if I was in class, I would just cover up the cubes with my hand, and I would write the first term as a minus b. So does that everybody see how I did that? So this actually does factor. And then the question is what's left. But everybody see how I got the a minus b there? So then a times what is a cubed? Well, a squared, right? And then minus b times what is b cubed? So it's going to be plus b squared at the end. So the only thing I got to do is figure out the middle term. So what I do is I multiply these together and I change that sign in the middle. Okay, so this will be plus a times b, and then it'll be plus b squared. Here's a minus b times the quantity a squared plus ab plus b squared. And if you don't believe me, you can go ahead and multiply this out using the distributive law twice, which doesn't have a fancy name like FOIL because there's a trinomial for the second one. But multiply each of those through there and combine like terms, and it's going to end up simplifying to a cubed minus b cubed. Okay, very similar. So the difference of two cubes also factors. So does the sum of two cubes. So the sum of two cubes factors. I'm just going to ignore the cubes, and I'm going to write a plus b. So once again, after that, a times a squared is going to give me the a cubed back, right? And I still need the plus b squared at the end, because b times positive b squared is positive b cubed. And then what I'm going to do is I'm going to look at that middle. If I have a plus sign here, I got to have a minus sign there, and then I multiply them together. So a times b. So I have this. So these are some manipulation things that we can use, and I'm going to give you an example of this to find a limit before I move on to 1.6. So let's look at an example. What if I have the limit as x approaches 1 of x cubed minus, not 1, let's do minus 8 over x minus 2. Well, if I plug in 2, we get a 0 over 0, right? And that's a problem. So, hey, Hannah's joining. Watch this. I'm going to put this in. Is she back? Oh, well, too late.
Her Wi-Fi was bad.
Bad Wi-Fi.
Yeah.
Well, anyway, so we got this. Yeah, you can just give her an update on what she missed on the factoring there. But anyway, this is 0 over 0, so I need to manipulate. But this on top, this is the difference of two cubes, right? So what I can do is I can try and factor that out. So factoring is a good deal. So I can write this as the limit as x approaches 2 of x minus 2. So this is really, I can write this right, as x cubed minus 2 cubed, right? And so the x minus 2 is writing that without the cubes there. And then it's going to be x squared. And then I'm going to have a plus 2 squared at the end, but that's going to be a plus 4, right? So minus 2 times plus 4 gives me that minus 8. And then what I got to do is I got to change that sign. So that's going to be plus, and then multiply these together. So 2x. So once again, you can verify that if you multiply that out using the distributive law and combine like terms, that you end up with x cubed minus 2 cubed. And then all over x minus 2. Now if I do that, which I have there, so now what I can do is I can go ahead and cancel these out. And so it's going to be equivalent to the limit as x approaches 2 of just this thing. And then now that's a polynomial, right? So then I can plug that in. I'm skipping a little sign. So normally I write is equivalent to the limit as x approaches 2 of what's in the purple box there. But then I'm going to just say equals, this is a polynomial. So I can just plug in, right? 2 cubed is 4. 2 cubed is not 4. That is horrible. 2 squared is 4. Plus 2 times 2 is 4. And then plus 4. So what do we end up with? The final answer for our limit is 12. So the limit as x approaches 2 of this quotient here actually exists and equals 12. So that's another way you can manipulate. So factoring, multiplying numerator and denominator by conjugates, things of that nature is always going to help us try and come up with a limit when you end up with an indeterminate form. I'm going to show you an easy one because some people try and do that stuff when you don't have to. If I just have, for example, the limit as x approaches 1 of x squared minus 2x plus 3 over x squared minus 4. Some people may try and factor this and stuff and see what cancels, but here really I can just do limit of the quotient as a quotient limit, and then I have polys, right? So I can actually just take the limit on the top, plug in 1, I get 1 minus 2 plus 3 is 2. And then on the bottom, if I plug in 1, I get 1 minus 4, which is negative 3. So I get negative 2/3 is the limit. So there was no need to factor, although I could factor the denominator anyway as x plus 2 times x minus 2. This one didn't factor that way. Now, if I had x squared minus 3x or plus 2x minus 3, that would factor, and we may end up with a 0 over 0. But in this case, we don't get a 0 over 0 form. And by the way, it doesn't matter if it's 2 over minus 3 or minus 2 over 3 or minus and then 2/3. I don't care if the minus is on top, on bottom, or out front. They're all equivalent answers, right? Because positive divided by negative or vice versa is negative. And this is the opposite of positive divided by positive, which is also negative. All right, so hopefully all that makes sense. So I'm completely done with 1.4 and 1.5. And then 1.6 and 1.7, are kind of versions of this with some other limits, one-sided limits. So I want to introduce you into that. And I'm still working on some Khan Academy stuff. I think those are some quick hitters that'll be nice to also step you through. They do have an epsilon delta explanation on there as well, besides what I've done that you may or may not like, but just some supplemental resources there. All right, so anyway, let's go to section 1.6, and this is one-sided limits. So instead of approaching from both sides, one-sided limits. All right, instead of approaching from both sides, we're only going to approach from one side. So let's look at kind of learn by here. Let's let f of x equal the square root of x, square root of x plus 1 if x is greater than 0. Let's let it equal 0 if x equals 0. And let's have it be x minus 1 if x is less than 0. I think I kind of looked at it, but this is a piecewise defined function. Okay. So what we're going to do, let's go ahead and graph that. If x is 0, I'm at 0, right? So the origin is part of my graph. But then I'm also going to look at, if I'm to the right of 0, it's the square root of x with an upshift. Whoops. So this is going to be an open dot here, open dot, and then the square root of x is half a parabola turned on the side, but it's an upshift up 1 unit. And then also on the left, so red from the right, I like red from the right. I don't know, we use green from the left. If I plug in 0, I get -1, but of course it's not going to equal -1, so that's an open dot, and then I have a line with a slope of 1 there. Okay, so that's this one here if x is less than 0. So what I can say here is I can look at different limits. So if I approach from the right at 0, if I approach from the right, the right-handed limit, the limit as x approaches 0 from the right, I put a little plus sign like in the exponent spot. I know I showed you this before, but kind of reminding you. Anyway, of f of x, this actually exists, and as I approach 0 from the right, my height approaches that red open hole of 1, because I'm on the red graph there, so it actually exists and equals 1. So this is called the right-handed limit of f of x, right-handed limit. And of course, as a mathematician, I don't like that, so what are we going to call it? RHL, for right-handed limit, correct? We also have the left-handed limit as x approaches 0. So if I say the limit as x approaches 0 from the left, hopefully you can see that, but there's a little minus sign in the exponent. Once again, it's of f of x, and I'm using here, but as x approaches 0 from the left, what's my height approach? My height is approaching that open green hole, which is a height of -1. So this is the left-handed limit. I'm out of room, so I'm not going to write that out, but that's the left-handed limit as x approaches 0 of f of x, where f of x is this piecewise declining function. So then what I'm going to say now, we also know that f of 0 does exist and equals 0, so we know that, right? I'm just going to put a little check mark there. We know that. However, the limit as x approaches 0 from both sides of f of x does not exist. So D and E for does not exist. So because the right-handed limit does not equal the left-handed limit, the limit on both sides as x approaches 0 does not exist. Now that's not true everywhere, because if I had, like if I'm over here at 2, I could say the limit as x approaches 2 from both sides of f of x. Well, that exists and equals 5, right? So basically, as I approach from the left and from the right, I'm going to approach that same height. So this exists and equals 5. In other words, it was okay. Limit of the root is the root of the limit. I could plug in not 2. My goodness, it doesn't equal 5. If I plug in 4, the square root of 4 is 2. So I could plug that in and add 1. So 2 plus 1 is not 5 either. It's 3. Man, I'm way off. Hope you guys are sleeping right now because I just really messed that up. But as x approaches 4 from both sides, that limit would exist. I just happen to be on this function here, and limit of the sum is the sum of the limits, limit of the root is the root of the limit, and as x approaches 4, the square root of x approaches 2 plus 1 is 3. So anyway, hopefully I didn't gum that up too much for you, and that makes sense. So here is a let's look at a theorem, which is another proven fact. I'm going to go back to black. So theorem, the limit as x approaches a of f of x exists and equals L if and only if the left-handed limit exists and equals the right-handed limit, and those both equal L. So that's kind of the shorthand way to write that. So the limit from both sides, remember this is from both sides of a, of x equals a. The limit from both sides of f of x exists and equals L if and only if the left-handed limit and the right-handed limit both exist and are equal. So the other way to write this, if I wanted to, I could say the left-handed limit, limit as x approaches a from the left, f of x exists and equals the limit as x approaches a. Sorry, it's supposed to be right underneath that, from the right of f of x, and these both equal L. Okay. So anyway, so the left-handed limit, that should have been x approaches a from the left, should have been under the limit, but that's right. Anyway, those both exist and also equal L, and if that's the case, then I can say the limit from both sides exists and equals L. So let's look at a quick example of this. By the way, I'm not going to have time to do epsilon delta in section 1.6, but I will do that tomorrow. Tomorrow's normal time. once again, wherever you want, if you're comfortable doing it in the room when you're at school, go to the room. You can chat with me there. If you'd rather be in the library, that's fine. Just let me know. Those of you that have to be home or quarantine, do it from there. But I will remote present all week for sure, and probably into next week. Okay, so another example, if I look at if I let f of x equal split function here, so absolute value of x if x is greater than or equal to 0, and minus x squared if x is less than 0. Well, let's graph that thing. So the absolute value of x, well, that's just dumb. That's just like x, right? This might as well be x for this one. That's that one. And if I do the left side, minus x squared looks like that, right? And then, of course, at x equals 0, I'd be at the top one. The absolute value of 0 is 0. So in this case, the limit as x approaches 0 from the right of f of x, that'd actually be the absolute value of x. So that'd be the absolute value of basically a very tiny positive number. Anyway, but that ends up being 0. And then if I look at the left-handed limit as x approaches 0 from the left of f of x, well, that's going to be this one. So minus a positive 0 squared, which is minus a positive 0, but basically it converges on 0, right? So if you're getting closer and closer to 0, it doesn't matter if it's positive or negative, it's approaching that height. So therefore, because the right and left-handed limits both exist and are equal, therefore, so 3 dots means therefore, the limit as x approaches 0 from both sides of f of x also exists and equals 0, which by the picture makes sense, because as I approach 0 or x equals 0 from the right, my height approaches 0 from the right, and as I approach x equals 0 from the left, my height is following this red graph into that as well. Even if I wasn't defined at x equals 0, if I had a hole there, it would still be the limit. Remember, the limit is you can get as close as you want without touching it. Okay. Section 1.5, we'll get into infinite limits. There is one that's awkward in section 1.6. So let's look at that. That's number 31. Number 31 basically has a couple of things here. Let me see if I can get it. This is section 1.6. Number 31. So basically we have f of x equals x squared if x is less than or equal to negative 2, sorry. It equals ax plus b if minus 2 is less than x is less than 2, and it equals 2x minus 6 if x is greater than 2. By the way, all right, there's our 2-minute warning here. So I'm just going to give you a quick sketch on this. Basically, if I were to graph this, we would have at negative 2 and then up 4, basically I would come into this, and so it would be a parabola there, and that hole right here, and then what I would have at over 2 down 2, I would have a line going this way, so be a line, so that was the line 2x minus 6, so it has a slope of 2, and the question is, what is in between? And so in between is ax plus b, so the only thing you know is that is a line connecting these points, and they want you to figure out what x equals a and x equals b is. So f of x, the purple one is x plus b. So the question is, how could you do that? Well, I've got 2 points, right? So you can use equations for that. So if you get a chance, I want you to work on this and try and come up with A and B are. There's a couple of different ways to figure this out. One way is actually a little easier, more convenient than the other. But anyway, what we end up here is we need to figure out what would actually allow the right and left-handed limits at -2 to be equal, and the right and left-hand limits at x equals 2 to be equal, and what would the values of a and b be to have a line that connects those dots and closes off the graph so that those limits exist. So that's number 31. That's one that maybe is just a touch more awkward, but also, you know, number 35 is a good one to look at, and one's similar to evens that you're going to have to do. All right, so I am done for today. And everybody good? And I'll stick around if you got any questions or want to chat on anything. So 1.4 and 1.5, the evens that are on your assignment sheet, I want those by 1:15 tomorrow, emailed to me. And then read and work in 1.6, especially the ones that are not the epsilon. I'll go through the epsilon delta stuff of section 1.6 tomorrow. So just practice stuff in 1.6. And if you want to read ahead in 1.7, that's fine too. So everybody heal up, stay safe and healthy, and we'll go from there. We'll talk to you later.